Thinking about math in terms of formulas is probably going to be a new method to you, but it's going to be extremely important to keep track because there are bad habits that people walk in with, and those are the things that I would call using a false formula, and there are good habits, which I would call using a true formula. And a lot of the early issues in an algebra class could be really formulated this way, and I've been in the past in a situation where I say, oh, that's not a thing, and then haven't had a good way to explain why it's not a thing. And so this true formula versus false formula thing, it creates the language necessary to be able to talk about why this works and why that doesn't work. And this is going to be strange, but it's going to be extremely helpful to think about it in this method. The natural instinct for students to say, oh, I just don't think about this in terms of formulas, but I want you to please try. Um, I will be asking a lot of things related to these formulas, and students have found this helpful in the past. So let's just take a look at this. So x times quantity y plus z equals xy plus xz is a true formula, while y plus z quantity to the x power equals y to the x plus z to the x is false. So one formula is true, one formula is false. You'll notice we've actually seen both of these formulas just with different variables, and the whole point in using these variables here is that in the first case x distributes and the second x does not. So we can't just say that x distributes all the time, right? So the argument for why in the first formula, we can't just say this formula is true simply by saying x distributes or distributive law, because the second formula, that you can't also explain that being true as x distributes, because x doesn't distribute there. So here's the thing, a true formula has to be true all of the time, no matter which numbers are plugged in. Therefore, the argument to show that it's true can't involve plugging in numbers. On the other hand, a formula is false if it's false just once. So the argument can involve plugging in numbers. So let's talk about what I mean by false formula, and don't ever use a false formula. Here's an example of some that kind of thing happening. I've seen this kind of mistake happen a lot. Or I don't know if mistake is the word, but perhaps misconception is the word. So, I've often seen this. So turning c plus 3 quantity squared into c squared plus 9. This to me is somebody, applying this exponent of 2 to the c and then to the 3. So if somebody showed a little more work, they might even write c squared plus 3 squared, and but often people even skip the step of showing the 3 squared and just writing a 9 instead. This is not a story about how much work is shown. This is a story about the work is just incorrect, right? So this is using the incorrect formula, or the false formula, of trying to distribute the exponent. So that can't be done here. To show that this formula is false, you select numbers for the variables and then simplify the left side using the order of operations, and also simplify the right side according to the order of operations, and you'll see that the left and right side will give you different numbers. So just as a summary list, here's some formulas we've shown to be true so far. You'll note that just for one of these, I've just swapped the two sides, or rather, sorry, in blue here, we haven't really, I guess, covered this explicitly, except, the A that's outside parentheses doesn't have to be written to the left of the set of parentheses. It could be written to the right. Okay, so anyway, here are formulas we've essentially shown to be true, and the acceptable reasons these formulas were true did not ever involve plugging in numbers. Sure, we might have plugged in some numbers to just discover what was going on, but the actual explanation that I will accept does not involve plugging in numbers for these. So instead, each formula has its own discovery process. It's kind of unfortunate that each has its own, but if the process of discovering a formula is true, that literal exact same thought process couldn't lead to two different conclusions, right? So each formula, unfortunately, has its own discovery process. Some involve geometry, some involve cats and boxes, some involve pizza. And then I'd like to make some clarifications about using formulas even further. This is the most important thing, the groundwork for what we do throughout the entire semester. You'll notice that this true formula and this false formula, let me point out some similarities. Both have y plus z in parentheses. Both have an x that's outside parentheses, but the difference is x is multiplied by quantity y plus z in the true formula, and x is an exponent in the false formula. So to really, really clarify, I want you to really understand this distributive law as presented here, to think about this in terms of a formula, and to think about every time you do the distributive act as really applying this formula. If one thing, let's just call it y, is added to another, let's call it z. So you got one thing plus another, and that's what is represented here in parentheses, y plus z. Then that quantity, while in parentheses, is multiplied by another thing, which is called x here. So x times um, so, I'm thinking of the y plus z first because it's parentheses. So you've got a first thing, let's call it y, plus a second thing, let's call it z. That result in parentheses is multiplied by a third thing called x. Then the whole point is that x times quantity y plus z can be rewritten as or replaced with xy plus xz. You can also do this in reverse. All of these true formulas work in reverse. That is, if you have an expression of the form xy plus xz, you can replace that with x times quantity y plus z. Okay, the important thing about xy plus xz is that the same quantity, here it's called an x, appears right there and right there as well, appears in the term before the plus sign and appears in the term after the plus sign. Okay, so this is all to say that if you have a true formula and all you do is swap the left side and right side, what's to the left of the equals and what's to the right of the equals, and you just switch the places of those, to me, they're considered the same formula. So please be consistent when you use a true formula. Be consistent with what is plugged in for each variable. So notice that the true formula up here has one x on the left side and two x's on the right side. And so there's a total of three x's, right? One here, second one there, third one there. You do have to plug in the same thing for all three x's. Technically, there's a lot more parentheses than we care to admit. And in the upcoming example, we're going to put in all of the parentheses which are technically there. So this is going to look a little strange at first, but there's a good reason to at least understand that these parentheses are here. I'm not expecting you to write in all the parentheses we're about to talk about, but it's good to know. It's good to know that they're there because there are times that we need to bring up the fact that there are technically these parentheses. So first of all, note, if I just switch out all the x, y, z's with p, q's, and r's, then I have p times quantity q plus r equals pq plus pr. That's the same formula, just with different variables. Okay, so we'll do it in that form. And how do you use a formula with all of that parentheses business? This is going to look really strange. This is going to be, I'll have to admit, a little tedious, but I want to go through this so that you really get a sense of what really happens using formulas. And then we'll talk about how to be a little lazier after this. Okay, so in a given expression, what you should do is insert a set of parentheses that doesn't change the expression's value. That's a key thing, and we did in earlier assignments talk about, can a set of parentheses be inserted without changing the value of the expression? Then the part in parentheses will be modified using the formula. So for example, let's say you have this given expression, 3 plus 5x plus 10y. You can insert parentheses here just around the 5x plus 10y part, and that's not going to change the overall value because one thing's being added to another is being added to another. So then this part that's highlighted in yellow is the part that we will modify using the formula p times quantity q plus r equals pq plus pr. This is in part why the insertion of parentheses exercise earlier was important, right? So we looked at, are these expressions equal or not based on insertion or deletion of parentheses. Then the part that we're going to modify, which is shown here in yellow, we have to determine if that looks like the left side or right side of the formula. What we have, for example, here, 5x plus 10y, it really is in the form pq plus pr. It's actually easier to see this if we first rewrite it as 5x plus 5 times 2y. Now, again, there's a lot of steps that I'm trying to demonstrate here. So we should identify what to plug in for each variable. And each of the plugins that you do should be in parentheses. So for looking at 5x plus 5 times 2y, look at how 5x plus 5 times 2y looks like the right side here. So the p, the repeated thing here, there's a p and then there's a p. That should be 5, technically in parentheses. Q is played by this x, and so that's x technically in parentheses. And then r over here, well, in the position of that, that's this 2y, which it's already in parentheses, but again, just technically in parentheses. So then, since what we have, 5x plus 5 times 2y, looks like p times q plus p times r, now we rewrite this to look like the other side, so we're going to make it look like p times q plus r. Right, so using the other side of the true formula, and then we'll remove any parentheses that we can. So I know it's real messy. The original thing that we had over here, just slightly rewritten with some parentheses and stuff. Looks like this. The 3 isn't changing, so we still just need to copy the 3 plus in order to get this equals to be valid. And then the part that's here, we rewrite by this format, and notice P is only written once here, so that's why there's only 1 5 here. Now this looks real messy, and then we just remove all the parentheses that are allowed to be removed while keeping the statement of what this expression is saying the same, and it will look like this. This is a lot of work, given that many people would prefer to just start with what's up here and just write what's down there without showing any of this extra work with parentheses. And that's normally going to be allowed, but you just had to see all the detail at least once here. Okay, so the thing to really clarify is that 5x, let me say it this way, 5 times x plus 5 times 2y is truly of the form p times q plus p times r. You've got to identify that the p's, look here and there, are like, or that's what the 5s are. And then q is x, and then r is, well, it's a bigger thing. R is 2y here. I hope this color coding actually helps the process. So the expression we were looking at is here with some color coding of like a purple, and so the P is purple, and then X is a red, and that's what Q is, and then the R is in a blue color, like this 2Y here. So the point is, let's take a look at these, colorful boxes, and if we did not look inside the box, in each case. If we don't look at the 5 inside the box, just say this is a purple box, right? Like maybe this box is sealed up with tape, so we can't see the 5 inside right now. Whoops, I don't know what happened there. Okay, then we have purple times red plus purple times blue. And that's what the format of the formula was trying to get at. So the formula is trying to address if you ever have purple times red plus purple times blue, that's one side of what the formula looks like, and you can convert what you have inside your problem to look like the other side of the formula. Okay, one of the key things is that everything that in the part that you're modifying, everything has to be counted for, or let's say put in a box. So here's another true formula. Root a times b equals root a times root b. We haven't learned why this is true yet. We will learn it later. But for now, let's use this to rewrite root 5 times x times y cubed. Now, let's see how this will not work. So you cannot rewrite this as root a times b using a is just x and b is just y cubed, because what happens is if a is x, and I've highlighted plugging in x for a in yellow and then plugging in y cubed for b in green, the problem is the 5 is missing, right? The 5 has not been accounted for. It is not boxed, it is unboxed. And when you use a true formula, you need to account for everything. Here's another way this doesn't work. You can try a is 5x and b is y, but now the cube is missing, right? The exponent 3 is unboxed. One thing that does work, here's a way that this will work, is you can say that root 5 times x times y cubed is in the format root a times b, where a now is this more complicated thing, 5x, and b is also kind of a complicated thing, y cubed. And take a look at how, see, this root 5 times x times y cubed is in the format root a times b. Right? If you don't look inside the boxes, both of these would read aloud as square root of yellow times green. And this means that we can apply this formula, so we can rewrite root 5x times y cubed, which looks like this left side, and we can rewrite it to look like root a times root b instead. So we won't go through that right now. Let's instead just talk about why all this mess with parentheses and so on. Good habits are important. Now there are times that we just don't write some of the parentheses, but why should we even talk about these parentheses? It's because they're technically there. So let me say why. In the order of operations, parentheses help protect the value of what we're plugging in. The parentheses that surround part of an expression are used to say this thing, the thing that's surrounded in parentheses, is a certain number. So here's a quick case study to show. A thing that people often try to do, which is actually an error, is they'll take this 3 and try to distribute here 3 to the x and to the 10, but the problem is there's this exponent 2 that does not allow you to do this. So somebody tried to let's really break this down. Somebody tried to apply a times quantity b plus c, that's one side of the distributive law, to 3 times quantity x plus 10. I would admit it looks like that, but the square is an issue. the real point is that if you tried to insert a set of parentheses to where you'd like to modify the expression, you'd have to insert a left parenthesis before the 3 and then insert a right parenthesis right before the square. But the problem is, as soon as you insert those parentheses, you've changed the value of the expression. Right? This is all why we were talking about, can you insert these parentheses or not? Inserting these parentheses leads to different values, and the portion highlighted in yellow is what somebody tried to modify using the distributive law. Okay, here's a second case study. This is maybe a smaller example to really show why parentheses really matter. But if you had x is 5 plus 10 and y is 3 plus 1, look, all numbers, what's x minus y? The thing is, even x minus y, even just these single variables, they're technically in their own hidden set of parentheses. And this really matters because you're going to have 5 plus 10 in parentheses there to replace the x, and then y is 3 plus 1, so y in parentheses gets replaced with 3 plus 1 in parentheses. If you simplify what's in parentheses first, you'll have 15 minus 4, and that'll simplify to 11. Sometimes the error that people will try to make is to do all of this without any parentheses at all, and they'll just write 5 plus 10 minus, they're copying the minus sign, and then the y here, people will tend to replace with 3 plus 1. And let's just take a look at what we get from this. So, well, read all plus and minus signs from left to right. So we'll simplify this first plus, and we'll have 15. Still copy the minus 3 and plus 1 to make this apparently equal. And then now this minus happens before this plus, because you just do pluses and minuses with the same precedence from left to right. And so that would give you 12 plus 1. That'll lead to 13. Look, that's a problem, isn't it? So something is wrong here. Which of these is correct? It's actually 11, because when plugging in for x and y, you need parentheses. Okay, so sometimes you will use a formula to just rewrite part of an expression. We sort of already previewed this, but for instance, if you were given 5 times x plus 13, you might choose to rewrite this as 5x plus 10 plus 3. So 13 got replaced with 10 plus 3. And then I will, just to form the good habit for now, you might skip this step later, but for now, let's insert a set of parentheses. This inserted set of parentheses did not change the value. And the point is, what's in parentheses right now, 5x plus 10, you can rewrite using the distributive law. It's sort of the backwards version of this, right? So the point is, maybe to make it look more like using the distributive law, let's rewrite the 10 as 5 times 2. Now take a look. Look at this formula. A times b plus c equals a times b plus a times c. This right here, or sorry, the part that's in parentheses, I've highlighted it in yellow over here. That looks like this, right? 5 times x plus 5 times 2 looks like a times b plus a times c. And so we'll rewrite, copy the plus 3. That's not participating in the distributive law, so we just copy the plus 3. But then this 5 times x plus 5 times 2, it looks like what's in the yellow box, and it gets rewritten in the format a times quantity b plus c as 5 times quantity x plus 2. Finally, there is one set of parentheses that we can just remove without changing the value and doing anything else procedurally. So in the end, we have 5 times quantity x plus 2, close parentheses, plus 3. So 5x plus 13 is equal to 5 times quantity x plus 2, close parentheses, plus 3. I know that looks like a lot, and there are ways to do this, writing fewer sets of parentheses. I'm not expecting everybody to show all this work all the time, but this work is all technically there all the time. It's important to know that these parentheses are behind all of the things that are going on.